property which is called as best linear and unbiasedness. So they are best because out of the class of all the linear unbiased estimator, it is the OLS estimator which gives the minimum variance provided all the assumptions underlying OLS are satisfied. Now, a very crucial question that arises, and that question is about how exactly or how do we know if the assumptions underlying OLS are valid for a given data set that is in front of us. How do we know the properties of these unobservable disturbance term, which we do not actually observe, but we still assume something about the probability distribution of these error terms? How do we know which variables are relevant, which variables are irrelevant, कौन से variable को actually हमें data matrix में लेना चाहिए? And if we've decided on the number of variables to be included in the model explicitly, what functional form should I use? So, all such questions which are or which moves around the idea of satisfying the OLS assumptions, if any of these are not satisfied, what we encounter is called as specification error. So, again, if you actually go back to our class and remember, we discussed about the assumptions of OLS. I need not repeat them again and again, but you know that the specification of your linear regression function depends on the probability distribution of the error term and the linear combination of the data matrix that we have. So let me just start the whiteboard. Write the equations. 1 second.
Sir, could you please start recording the lecture?
Yeah, I'll do that. Can you see the screen now, all of you? Can you see the screen?
Yes, sir.
Okay, all right. So if you actually remember, this is the population regression function that we have. So the specification of our linear regression model centers on how these x's enter into the equation and the form of the probability distribution of the error terms. And also one very crucial thing which we often take for granted is that while we run an OLS estimation to talk about, or to estimate a causal relationship between two or more than two variables, all the time we take it for granted that this parameter beta remains constant for the entire period of observations. However, your betas might change. That is, the parametric relationship between x and y can itself change. And one very practical example that you can think which pertains to Indian economy itself is that, prior to 1991, the marginal propensity to consume, if I'm estimating a consumption and income relationship for India for the period 1960 to 2020, or let's say 2010, what a huge change post 1991. So if we keep
We
on,
lost the audio for a while.
am I audible now?
Yeah, you're audible now, so yeah.
Actually,
We said
there's
last thing we heard was 1991, and then it
okay,
cut off. MPC in 1991.
okay. So there's huge connectivity issue at my end. Okay, so what I'm saying is that if you're estimating a relationship between consumption and income for Indian economy, let's say for the period 1960 to 2010. So after India initiated economic reforms, the income levels have gone up. Also, more or less now we have more of a become a consumption-driven economy. So the marginal propensity to consume out of an additional increase in income might be very different to that of India pre-1991. So if you're running a regression equation for the entire period, let's say 1960 to 2010, and if we just have one parameter for the entire period, this might be wrong in our part. So the entire specification of the linear regression rests on how x's enter the equation, whether there are any structural break, that is whether betas have changed, and the form of the probability distribution of the error terms. So the moment I talk about that the specification of linear regression equation depends on these parameters, it means if there's any problem which pertains to either the residuals or the error term or the explanatory variables in the model or the parameters that have been used in the model, if any of or combination of such things go wrong, what we encounter is a specification error. So is specification error mein, you'll have, let's say, start talking about iska assumptions. I'm not writing again and again, but I assume that you are well versed with the assumptions of a linear regression model. Your x's are non-stochastic, your errors are have mean zero and unit variance. They are also normally distributed, and there is zero correlation between the error term and the regressors that have been used in the model. And x must have the full column rank. So these are the assumptions that actually defines the OLS method of estimation. So now let us talk about what kind of possible problems that one might encounter as far as OLS regression is concerned. So let's say you might have, let's discuss about the possible problems with the error terms that we have. So सबसे पहला क्या है assumption मेरा assumption था that error terms are identically and independently distributed with mean zero and unit variance. And if I add the assumption of normality into this, then what we say is that error terms are normally distributed with mean zero and variance 1. Time and again I have repeated that this normality assumption is not required to talk about estimation of OLS estimators as far as is concerned. The normality assumption helps us in drawing an inference, because in that case, even under the small sample, we can draw an inference based on the normal distribution of the error terms. However, if the error terms are still independent and identically distributed, but they are not normally distributed, wrong with the OLS estimators? The answer is that if the error terms continue to be independent and identically distributed, as far as this is correct, and if it does not follow a normal distribution, then there's this very useful rule in statistics that if there's a non-normal distribution, and if you keep on increasing the sample size, what happens is that the first and second parameter of distribution, which is what I mean by mean and variance. So measures like variance and mean of any non-normal distribution tends to become a normally distributed random variable when the number of sample size increases to sufficiently large. However, there's this one common misconception that people, or you might find sometimes written in textbooks as well, that any non-normal distribution tends to follow a normal distribution as the sample size increases. But always remember that it is only the first and second moments of distribution which converges to the normal distribution, and the third and higher order moments of distribution need not converge to normal distribution for any non-normally distributed random variable. But as far as inferences are concerned, we are only concerned with mean and variances. That's why it suffices us to understand that a non-normally distributed random variable will follow a normally distributed random variable when the sample size increases sufficiently large. So if the errors are not normally distributed, what will happen is your OLS estimators still remain efficient, still they are unbiased estimated, but the inferences that we draw out of these non-normally distributed error term will only be valid in large samples, or they are also called as they are only valid asymptotically. Why I'm saying that? Because the inferences that we draw based on the small sample will be drawn out of a non-normal error distribution. So if the number of sample size increases sufficiently large, तब जो हमने inferences draw किया है, that will be valid. So your OLS estimators remain unbiased, it remains efficient, it remains consistent, but inferences drawn out of the non-normally distributed error form or error terms are only valid asymptotically now. Asymptotically means for large samples. So it is not that much of a problem as far as specification error is concerned. Now, if you remember, the second assumption that we make about the error term, which is called your assumption of spherical disturbances. So assumption of spherical disturbances में क्या है? Your error terms or your error are homoskedastic and they are non-autocorrelated. So combination of these two assumptions, they are called as your errors are spherically distributed. Spherically distributed, that is, you have a nice symmetry around the mean and variance of the error distribution. The variances of the errors are constant across all the observations, and they also tend to be not correlated with each other. So an ideal form of error distribution, that's what we assume as far as OLS is concerned. So obvious है कि अगर इनमें से ये assumption या दोनों अगर valid नहीं है for a given data set, then what you encounter is a specification error based on the residuals of the regression analysis. So violation of assumptions of homoskedasticity is called your heteroskedasticity, which is what we'll talk in today's session in great detail. So how do we write variance covariance matrix of the error term as? We write is an expected value of U transpose as all the principal diagonal elements, they are sigma square, and all the non-diagonal elements which represents the correlation between the error terms themselves, they are 0. This is what the assumption of spherical disturbances are. So we say that error terms have constant variance, have same variance across all the observations, and they also tend not to be correlated with each other. So the combination of this homoskedasticity and non-autocorrelation is termed as spherical disturbances. And if this assumption gets violated, terms still continue to be correlated, but the variances of the error terms are changing. So in that case, what will happen is your off-diagonal elements will still continue to be 0, but your diagonal elements will now have a subscript attached to it, that is sigma 1 square, sigma 2 square, sigma 3 square, and so on and so forth. So what it tells you is that error terms now no longer have constant variances. And we'll talk about heteroskedasticity. Yeah.
It will be
Sir, could you please?
Again, you lost your voice?
बोलो तो. हाँ, yes sir. वो थोड़ा repeat ही करना फिर. हाँ sir, हाँ sir.
Okay. Which portion you lost my voice?
So when it violates, like when it violates the homoskedasticity.
Yeah. So violation of homoskedasticity, what it means? It means homoskedasticity क्या है? Equal variances across all observations. That is, your variance of error terms do not change with changes in the explanatory variables. That is your number of observations. So across all the observations, your error terms have constant variance. That is the assumption of homoskedasticity. If it gets violated, it is called as heteroskedasticity. And if only error terms still continue to be non-autocorrelated, only the variances change, what we have is the presence of heteroskedasticity in the OLS model. If your error terms also are autocorrelated, autocorrelated means errors of this observation or current period observation tend to be correlated with past or previous observations, or they have some form of correlation with each other. That we have the violation of non-autocorrelation. In that case, we say that errors are autocorrelated. Now, a combination of heteroskedasticity and autocorrelated error terms, I'm sure that अभी आपने जो financial economics के लोगों ने जो exercise किया, they are mostly called as autoregressive conditional heteroskedasticity model, ARCH model, GARCH model, because in such models, your error terms, they are just not heteroskedastic, they are also autocorrelated with each other. So as long as either heteroskedasticity is there or autocorrelation is there, problem is not that much complex. But when you have combination of heteroskedasticity and autocorrelation, that's where we have to, be a little bit more cautious in finding out a remedial measure which removes this problem or which removes this complexity as far as regression equations are concerned. Now, बात आ रही है कि ये homoskedasticity or non-autocorrelation किन टाइप के exercises, किन टाइप के practical applications में it might you might encounter them. So mostly in cross-sectional analysis, that is when you're recording the number of observations across different sections. So in cross-sectional applications, the assumption of homoskedasticity tends to get violated more often than not. That is, your error variances no longer remain constant. इसका एक perfect example आप ले सकते हो. Again, the same example. Let's say income and consumption expenditure. So assumption of homoskedasticity, what it means is that not only the average value of consumption expenditure remains same across all income levels, but the variability around that consumption expenditure or that mean consumption expenditure also remains constant across all income levels. But in reality, if you go and collect data on consumption and consumption expenditure and income of different households in a locality itself, forget about two different localities. In a locality itself, what you'll notice is that consumption expenditure tends to increase with the income level, and not only just this, the variability of that consumption expenditure also increases with increases in income levels. also, if you again, let's say, estimate a relationship between the amount of expenditure incurred on vacation and income earned by a family, presence of heteroskedasticity will mean that across different income levels, the amount of expenditure or amount of vacation expenditure incurred by a family or a household also changes. So in most of the cross-sectional applications, what you have is the violation of assumption of homoskedasticity. That is, your violation of autocorrelation more or less happens when you have either, let's say, lagged values of the dependent variable itself in the as explanatory variables, which is what happened mostly in the distributed lag models. We'll discuss them. Or in most of the time series applications, you have violation of non-auto correlated error disturbances, and this is quite obvious as well. In time series observations, you have observations that are recorded on a specific date or a specific time, whether it's daily, yearly, second-wise, minute-wise, millisecond-wise, but they're recorded at a discrete units of time. So it tends to become more obvious that the current observation somehow gets determined by the previous observations. Some proportion of previous observations has a certain influence or impact on the value that you record for the current observation. And this is very valid when you have the stock prices data or any data which is a time series observation. So in that case, your error terms tend to be autocorrelated, tend to be related to each other. So as long as either of them are there, problem utna complex nahi hota hai. But when you have combination, and mostly in time series applications, you have this combination of heteroskedasticity and autocorrelated error disturbances. That's where it becomes more cumbersome. So this might be the possible problem that we have as far as specification error with regard to disturbances are concerned, and that too in particular the spherical disturbances assumption. Now, one last specification error that you might encounter as far as errors are concerned is your non-zero correlation of errors with the regressors. That is, if this assumption gets violated, what happens when you have non-zero correlation of regressors with the explanatory variables? And it might happen that your error observation tend to have some sort of correlation with the regressors that you have used in the model or explanatory variables that you have used in the model, because your errors more often than not they are a list of all the variables which either you could not enter them explicitly in the model, or there are certain variables which are very difficult to measure quantitatively, something like aptitude, something like all those latent variables which is very difficult to quantify. So there are many cases when we have a non-zero correlation of errors with the regressors. Now the question that arises over here is, when it is a serious breakdown and when it is not that serious. That is, serious breakdown means what? अगर मान लो कोई भी assumption यहाँ पे violate होता है OLS का, तो mostly हम में serious क्या होगा? या तो उसका जो estimation होगा, that will be, it will no longer be an efficient estimator, or it will no longer be a consistent estimator in the long run as well. And if it is not an efficient estimator, the inferences drawn on the basis of inefficient estimators tend to be inefficient as well. So as long as the current period error observations are not correlated with the current regressors that have been used in the model. Till that time, your OLS estimators definitely has a small sample bias, or it is also called as finite sample bias. That is, in the small sample case, when you have non-zero correlation of errors with the regressors, your OLS estimator will no longer be unbiased in a small sample, but it will continue to remain consistent. It will continue to remain efficient in the large sample cases, as long as the correlation that is there between the error term and the regressors, that does not happen in the current period observation. So it might happen, if you have used a lagged value of dependent variable itself as an independent variable, so that lagged value of dependent variable might be correlated with the current period observation, but as long as the current period explanatory variable is not correlated with the current period error observations, till that time this is not that much of a serious breakdown of the assumptions. But the problem becomes real is a consistent estimator, and that's why we must not use.
We lost your audio. The last thing we heard was the problem becomes really, and then it cut off.
Yeah. Okay, sorry. So the problem becomes really serious when you have the regressors, the current period regressors, correlated with the current period error observations. And we'll discuss this, and this mostly happen in case of simultaneous equation models. When you have a joint determination of variables, something like price and quantity demanded, which we'll discuss when we discuss simultaneous equation models. So this violation of non-zero correlation of error with the regressors in the current period observation is a much serious violation. And when such things happen, such things occurs, OLS no longer is an efficient, neither it's a consistent estimator. Consistency is a large sample property. So एक thing हमेशा इसको समझ लीजिएगा that if your estimators, even if it is unbiased, even if it is biased in a small sample case, but if it becomes efficient and consistent in the large sample case, your estimator is quite good. Because ultimately, whatever the use of estimators that we'll have, if you want to generalize anything on the basis of the estimators that we have estimated for a larger sample case, and if it is a consistent and efficient estimator in the larger sample, then our estimation remains fine. The problem occurs when your estimators no longer are consistent and efficient in the large sample case as well. So when you have non-zero correlation of regressors with the error term in the current period, which is what mainly simultaneous equation models are concerned with, OLS estimation should not be used at all. And that's why I'm saying that this is much more of a serious breakdown of assumptions. So as far as the specification error concerned with the residuals are concerned, these are the three possible specification error that we might encounter when we run an OLS method or OLS estimation. Now, apart from the error term that we have in the population regression function, we might encounter problems that are associated with the explanatory variables that we use in the model. Think logically, what might be the problems that are associated with this X? सबसे पहला चीज कि सपोज जो भी आपने पॉपुलेशन रिग्रेशन फंक्शन यूज किया है on the basis of your research, on the basis of theoretical implications, how do we exactly know, how do we exactly identify that we have included all the relevant variables? If you're trying to establish a relationship between two variables, x and y, or be it anything, be it unemployment, inflation, income, consumption, fiscal deficit, inflation, any economic, any macroeconomic variables, how can we be very sure that we have included all the relevant variables? So the first possible problems that you might encounter which are related to the explanatory variables in the model is called your exclusion of relevant variables. They are also sometimes called as omitted variables. So omitted variables, that is when we have, so suppose we are trying to establish a relationship between the price of a house, or we are trying to find out the determinants which decide how much price for a house should a consumer pay. Now there might be various determinants. Some of the major important determinants will be, the size of the flat, and that will be measured in the square feet. That is, how large is the flat depending on the square feet that, that's how we measure it. Then the number of bedrooms, if we have, let's say, 1 bedroom, 2 bedroom, 3 bedroom, 4 bedroom, 5 bedroom, it also, depends on that. The locality of the flat, and other variables which depend from theory to theory, which will determine the price of a house that a consumer is willing to pay. Now, if there is for a given location, for a given question that we have in our hand, if there is one particular variable which is very, very important, let us for the time being just take this proximity to the local market or local railway station or airport is one of the important parameters which ultimately determines the price of a flat that a person has to pay or is willing to pay. And somehow, since we are not able to either, on the basis of our theoretical research, we are not we have here is the problem of exclusion of a relevant variable. Now, this is a very, very serious problem which we'll discuss, when we come to discussing this particular part of specification error. The problem associated with exclusion of relevant variables are called as omitted variable bias. Because you ultimately say when we write the equation y beta naught beta 1 x1 plus beta 2 x2 plus so on and so forth y. Now, all these betas, they are partial regression coefficients. And what do I mean by partial regression coefficient? Partial regression coefficient, it tells us the impact of x1 on y, keeping all or in the presence of all other explanatory variables in the model. And suppose there was a variable which is a relevant variable. Relevancy of the variable will get decided by either the t ratio or the significance of that variable, or also on the theoretical implications, some experimental research as well. So if this, let's say if x2 was omitted from this regression equation, what will happen is this beta 1 in that case, it will tend to either overestimate or underestimate the effect of x1 on y in case of this x2 as a relevant variable omitted from the equation. We'll discuss this in greater detail, but this is how we understand this exclusion of relevant variables as an example. इसी का converse case will be inclusion of irrelevant variables. That is, even the variables, जो हमने कल example देखा था, that impact on sales through the advertisement expenditure on newspaper, it does not explain that large a variation on sales. In that case, if I included newspaper in my model, that will be an example of inclusion of irrelevant variable specification error. Now, this specification error is not that serious. It does not lead to biasness in the OLS estimators. So more often than not, inclusion of irrelevant variables we do not discuss that much because this is not that much of a serious problem. More often than not, by looking at the estimator sign, when we go for the diagnostic check of our model, and then we see that the variable need not be included, we simply remove that variable out. But exclusion of relevant variable is is of a much serious concern, and also why it's a much serious concern, you have to understand that this error term, I told you, it's a catch-all variable. All the variable which either due to the measurement issue or due to our research foresight, we are not able to include them explicitly in the model. All the variables are explained or are just included explicitly in the model in this error term. And then the assumption of non-zero correlation of errors with the regressors. In the presence of exclusion of relevant variables, this assumption will not get satisfied. Because if there was a relevant variable which should have been included explicitly in the model, and if it was not included and it has been included in the error observation, definitely the omitted variable and the included variable might have certain correlation which impacts much more the relation or this OLS model that we have run. And that's why exclusion of relevant variables is a much serious concern. And the last associated specification error that we encounter as far as the problems associated with the explanatory variables are concerned, which again depends on your theory and your research, is your incorrect functional form. Suppose y और x के बीच में semi log relation था. That is, let's say either y increases at a much faster rate or x increases at a much faster rate. If you plotted the data and still you run an OLS model only using the raw observations on y and x, in that case what you encounter is a problem of incorrect functional form. Again, let's say apart from just including x1, the model also required an inclusion of, let's say, x1 square term or an interaction term between x1 and x2. So all such problems which are associated with the functional relationship between y and x, that is incorrect functional form, and it is also a specification error. So for now we'll just not discuss the problems associated with the parameters. We'll discuss them when we talk about the parameter stability and all. But as far as specification errors are concerned, these are the specification error which is associated with the explanatory variables, which are much more important, and the errors of the regression. So if any of these gets violated, what we encounter is the problem of specification error, and that's why there are various tests to identify such specification error. And once you identify which specification error actually we have encountered, then we suggest remedial measures for the same. In today's lecture, we'll start with discussion of heteroskedasticity. That is what happens when we have presence of a heteroskedastic error term in the model. So I've shared a file with all of you. Could you please open that file and our studio as well, all of you? Once you're done, please let me know. Done? Guys, done? Can we start? Can you all hear me? Okay, all right. What I want you to do is, first of all, load that file onto your R. Yeah. Okay. No issue. So first of all, what we do is you just import that file onto your RStudio. Do that. How many of you know how to do that? Okay. Guys, is there anyone who does not know how to do that? Okay, all right. I'll just share my screen. Okay, can you all see the screen now?
Yes, sir.
ओके, ऑलराइट. सो आपने फाइल जहां पे भी सेव किया है, फर्स्ट ऑफ ऑल यू हैव टू अंडरस्टैंड दैट in order to load the data for the first time on R, the syntax that we follow, either you can use read.table, data frame. I have used read.csv. So you see, when you use this command, read.csv, you see the syntax. Can you all see the this yellow line that comes?
यस सर.
ओके, सो देखो पहले इस फाइल इस सिंटैक्स को एक्सप्लेन कर लेते हैं, देन यू कैन डू इट योरसेल्फ. सो read.csv के बाद आपके पास फाइल पूछता है, दैट इज पाथ ऑफ द फाइल. Right click on the file and then go to the properties and you'll see the path of your file. It will be on your desktop or laptop, whatever it is. So वो path हमें चाहिए यहाँ पे. Then header is equal to true means that जो आपका first row है, that is of the column names and names of the the various columns that we have separated. These things we need not use once we have read.csv file. So we are not going to talk about this. So now let us talk about how do we actually load this. So I have used this command and this date. I have stored this file as sorry. I have stored this file by the name data. You can use any variable name. So data as a variable has been stored as read.csv. The path name is double inverted comma c double dot users public. जो ये मेरे फाइल का पाथ नेम है. आपकी फाइल का जो भी पाथ नेम है आप वहां पे यू राइट दैट. देन लास्ट में जो फाइल नेम है वो .csv inverted comma closed comma header dot true and then you simply do it. Just follow this step and let me know if you are able to do that. Please say yes or no so that I'll move ahead. So read.csv, file path name, then the name of the file and comma header is equal to true. It will load your data set on R. Let me know when you are done, please. Done? Okay. All of you have loaded the data set?
Wait for a minute first.
Okay?
Yes, sir.
All of you?
Answer.
Okay, all right. Now, what I want you to do is, first of all, you have to understand the data. How do we understand the data? You look at the first 6 rows of the observation. यहाँ पे data ज़्यादा बड़ा नहीं है, तो you can simply use the view function as well, and have a summary of the data. So कल जैसे हमने किया था, please use those functions: head, data, and summary data. Once you're done, let me know. What I want you to do is, I want you to estimate a regression function for this data set. Then I want you to calculate the residuals of this data set, that is residuals of the regression line. And then I want you to plot the residuals against the explanatory variables. I'll repeat my question. First question is, you have to estimate the regression equation for this particular data set. Second is the question clear, all of you? Guys, can you hear me?
So we lost you between three.
Can you hear me now?
Yeah.
Yeah, the question is कि आपको पहले estimate करना है regression line. Second part is you have to calculate the residuals from the regression equation. And the third part is you have to plot the residuals from the regression equation against the explanatory variable. Is this clear? Is the question clear, guys? Or should I repeat it again?
Clear, sir.
ठीक है? तो please do this. We'll start talking about this in 10 minutes. So once you're done with this, we'll then discuss this. If you have any questions, please ask here. All right, done. Done, guys. Done? No? Yes? Anything? Maybe?
Yes,
Okay.
sir. Done.
Okay. So we plotted all the residuals again?
Yes, sir.
Okay. Very good. Thank you. So, okay, now, so what all we did in this, for this particular data set, we calculated the estimated regression equation. And so this is the regression equation that we got, the intercept and the explanatory variable. These are the associated standard error. Residual standard error is 1.314, adjusted R square, multiple R square, sab kuch looks really fine. So just by having the first look, we cannot say if the model suffers from any problem or such that. And that's why the first diagnostic check that we perform for any model is to analyze the residuals. And that's what we did. So we first predicted our data by calling this predict function. So the predicted values we got, then we calculated the residuals, that is the actual observation, that is the second column of my data set. That's why I use data. It will take the second column observations of the data set data minus of the predicted values. And then we have plotted the explanatory variable on x-axis and the residuals on the y-axis. Now, do you think there is some problem with this model?
Yes, so the variance of the error term increases with an increase in x.
Correct, correct. So what we notice here is that for higher values of the explanatory variables, the variability of the residuals in this particular case also increases. So it definitely violates the assumption of homoskedasticity as far as the variability of this or this plot suggests. It means there is presence of homoskedasticity, but just by looking at the graph of the residuals. We have not done any test or any formal statistical test so far. So the first thing that we do as a model diagnostic check is always plot the residuals. In this case, we just plotted the residuals against the explanatory variables to see whether there is any change in the variability pattern of the residuals with changes in the explanatory variable. So what we notice here is that for higher values of x, that is for higher values of income level for family, the error term or the residuals from the regression equation also increases. So it definitely suggests that there is some, or it definitely suggests that errors are not homoskedastic. That is, they do not have a same variance for all the observations. It means it definitely depends on the explanatory variable that we have used. That is, for higher values of explanatory variable, in this case income, the residuals tend to be higher, larger. So just by plotting the residuals against the explanatory variables suggests that there is a presence of heteroskedastic errors. Now, before talking about the various tests that we have for heteroskedasticity, one very common remedial measure as far as removing heteroskedastic errors are concerned is to apply logarithm to the variables. That is, you run a regression of log y on log x and then repeat all the things that we have done so far. So just do that part. You run a regression of log y on log x, then again calculate the residuals, plot the residuals against the explanatory variables, and just check whether you get any systematic pattern there also or not. Please do that. Done, everyone? Done, guys?
Done, sir.
Sir,
हाँ जी.
could you please scroll up this console?
Come again, yeah?
Could you please scroll up the console?
क्या हुआ मोहित?
सर वो कंसोल को थोड़ा ऊपर करना.
You are not writing yourself.
Sir, I lost my connection, so I'm not getting क्या करना है.
आपको क्या करना है? लॉगरिथम x और लॉगरिथम y पे रिग्रेशन रन करना है. ठीक है? Guys, what about others? At least say anything you have done, you have not done. I have just heard from Neil. And what about others? Okay, and Punjab has done. Shubham. Okay. So, do you see any change in the plot of residuals against the explanatory variables?
The values against the y-axis have decreased, but it is still splitting up towards the end.
Correct. Yeah. So, the purpose of this exercise was to just tell you that the first point that we have to always do is, after we have run the model, is to analyze the graph of the residuals. क्योंकि रेसिडुअल्स के ऊपर सारे assumptions हैं आपके errors के जो assumption है कि residuals must have mean zero. So just check whether the residuals that you have obtained for the regression equation has a mean zero or not. It must have a variance, a unit variance, if it is a homoscedastic error term. If it does not have a unit variance, or if it does not have a constant variance, then it must mean that errors do not have the constant variance. Now, one common exercise that we generally do when we encounter the problem of heteroskedasticity, it's a common understood term that we take logarithm of the variables that we have, then we run a regression on the log of the variables, then again we calculate the residuals, and then we plot the residuals against the explanatory variable. In this case, explanatory variable will be your log x. And then we check whether the residuals again follow some kind of systematic pattern or not. If it does not follow a systematic pattern, it means that you have removed the problem of heteroskedasticity. But if it still continues to follow, it means against the explanatory variable. But yeah, you lost me again?
Yes.
Naveen, you were saying something? You lost my voice again over.
Yes, sir. We have lost from sir that implementing log and see the graph, sir. After that, we have lost.
Actually, I'm not able to hear what you're saying. Can anyone else tell me where was I when you lost my voice?
So you were telling that how we see the systematic pattern for heteroskedasticity.
Okay, yeah. So after plotting the residuals, we see whether any systematic pattern of residuals you get, or the residuals do not show any systematic pattern. In that case, if it does not show, it means that you have somehow removed the problem of heteroskedastic error term. But if it still continues to remain in the same way, what it must mean is that you should take some other remedial measures to remove the presence of heteroskedasticity from your model. Now, the exercise that we did just now was to plot the residuals against the explanatory variables. And if you remember from our discussions on normal equations, the virtue of normal equations, by that virtue of normal equations, the non-zero correlation between the residuals and the regressors from the model are always there. So, if you're trying to test for the presence of heteroskedasticity in a particular model, it is better either to, so the normal equations only talk about zero correlation between the error term, that is ui, and xi by the virtue of normal equation. But your squared terms of error might be related with x, or error might be correlated with x of squares, or any other function apart from the linear function between u and x. It may suggest any form of correlation. So, the test procedures which are suggested to remove the presence of heteroskedasticity should ideally conduct a regression analysis of either squared terms of ui with x or mod of ui with x, or if you are conducting a regression using ui, then ui should be regressed on the non-linear function of the explanatory variables in the model. Because by the virtue of normal equation, there will be zero correlation between ui and xi. So if you are trying to test, if I trying to devise a formal test to detect the presence of heteroskedasticity in the model, the regression test should be designed in such a manner that you run a regression of either ui on non-linear function of x's or non-linear values of ui on the x's that we have. So it is in this line that there are 4 tests which have been suggested by different statisticians from time to time. There are other tests as well, but some of the tests which have become more famous are your reset test. It is also called as Ramsey test, Ramsey specification error test. Then you have White's test, White's heteroskedasticity test. Then you have Bruce-Pagan test. You have Goldfield quant test. And then there are other tests such as likelihood ratio tests are also suggested. We'll discuss these tests one by one by using again examples only. But before that, let us try and understand the theoretical underpinnings of all these tests. So we'll discuss 2 tests in this class today. And then for the same exercise, I ask you to conduct these tests and find out whether these tests detect any presence of heteroskedasticity in our model or not. So let me just present my screen. Yeah, can you see the screen now?
Yes, sir.
Oh, all right. So what we intend to talk about here is, first of all, we discussed what actually heteroskedasticity is. Okay, one more thing that I forgot to discuss. So heteroskedasticity kya hai, that we have already discussed. This is what heteroskedasticity is. The second thing is how, so once you know what heteroskedasticity is, the first thing is to detect it. That is, how do we actually detect the presence of heteroskedastic error terms? Once we have detected it, then we must answer what are the consequences of heteroskedasticity. And once we have discussed the consequences of heteroskedastic error terms, then the next thing that we are concerned with is the remedial measures. So it is along these lines all the specification errors we'll discuss. The first test will be the detection test. The second will be to discuss the consequences of heteroskedasticity. And the third will be to talk about the how actually we can use different measures so that we remove the effect of heteroskedasticity from our model. Right now we are at the first step, that is, how do we actually detect the presence of heteroskedasticity? So अभी हमने क्या देखा था example में, we plotted a residual from a regression equation against the explanatory variable, and just by looking at the plot of residuals, somehow we could convince ourselves that the errors do not have a equal variance for all the observations. That is, for larger values of x's, the value of residuals is quite large, and for smaller values of x, the value of residual is less. So obviously, when you have such large, variability in the observations concerning residuals, then the assumption of homoskedasticity somehow does not meet the criteria. Now there are 4 specific tests that have been suggested statistically. However, there are other tests as well. The first test is your Ramsey test. And also a test suggested by Anscombe. Second test is your White's heteroskedasticity test. Third is your Bruce-Pagan test. And fourth is your Goldfleck-Quant test. And there are other tests which we discussed as just a passing by comment. This is called the likelihood ratio test. I'm sure that from your undergraduate class you are aware what exactly White's heteroskedasticity test, what is Bruce-Pagan test, because they are mostly discussed in the undergraduate courses. Can anyone tell me what do you mean by White's heteroskedasticity test? Anyone? No? Guys, can you hear me?
Yes, sir, we can hear you.
Okay, so anyone aware of any heteroskedasticity test that we have written on the screen?
I did Goldfield quant test in bachelor's.
Okay, okay. What about you, Manda? Are you aware? Or do you remember any test?
Sir, I think for white test we use all the different functional forms in which the variables can be related with the error term, and then we run a chi-square test.
Correct, very true. Thank you. What about you, Neil?
So White's was that same one, and even in Ramsey you do a similar thing, but instead of different ways of X, you do with different types of Y.
Correct.
And and otherwise, sir, I'm not very sure. Sir, those are the ones I've read about.
Okay, okay. What about you? Anyone else would like to add? Bhushan, aware of any test?
No, sir.
Okay, Sharanya, what is Goldfield quant test? If you recollect something from your undergrad days.
So that's what I'm trying to recollect. I think it was related to we had to order, rank the observations from beginning to lowest, then omit a few observations and run separate OLS regression for some observations to, after splitting them, and then we had to find the F value and
Correct.
I don't remember it perfectly, but it was related to this.
Yeah. Very true. Okay, so we'll discuss these tests one by one, and for some of the tests, I also ask you to do this exercise for the example that we've just discussed. So Ramsey test and ANSCOM, a test suggested by ANSCOM. So अभी हमने क्या देखा, अगर हम regression procedure use कर रहे हैं to detect the presence of heteroskedastic error terms in the model, then that regression should always be a regression of linear term of u on non-linear term of x's, or a non-linear term of u on linear terms of x's. So a non-linear term of u and non-linear term of x's, the very simple form of non-linear form of x's have been suggested by Gletzer, where he does not talk about any non-linear powers of x's. Instead, what he suggests is you run a regression of mod of ui on different non-linear functions of x, whether it is 1 upon x or 1 upon root x, or mod of ui, you run a regression on x, and so on and so forth. But as far as these tests are concerned, Ramsey and ANSCOM, they both have suggested running a regression of the residuals that we obtain, that is ui, on the predicted values of y from the regression. That is, to run a regression involving ui hat from the, I'm using hat for the residuals, on the various powers of the predicted values of the regression. That is y hat square, y hat cube, and so on and so forth. Now basically Ramsey test and ANSCOM test is suggested when you have a multiple linear regression model, because ideally logic kya hai? Logic still remains the same, that normal equation implies zero correlation between the residuals and the regressors. That's why you run a regression of ui on various non-linear powers of x's and various other combination of, so instead of using powers of x's, which they say becomes really cumbersome, what they suggest is that instead of power of these x's, we must take the predicted values of the regression equation and run a regression of ui on square of this y hat or cube of this y hat or some other non-linear power of y hat. And then run this regression and test for the coefficient. That is, what this suggests is that ui hat is equal to beta naught plus beta 1 y hat square. देखो y hat का term नहीं आएगा क्योंकि ui hat and y hat will be y hat will be a term that will have xi, and since ui and xi will have a zero correlation, that's why we will not be using the term y hat if you are using ui hat on the left hand side. So ui hat is equal to beta naught plus beta 1 y hat square, beta 2 y hat cube plus let's say ui. Now the only question that arises is that how many non-linear powers of y hat should we use? इसका कोई hard and fast rule नहीं है, neither इन्होंने कुछ बताया है. So once you run this regression equation, the null hypothesis becomes that beta naught, beta 1, beta 2, all of them are combinedly equal to 0. That is, the entire model is insignificant. Now what it will suggest, if the coefficients are individually or combinedly insignificant, what it means is that your error terms are homoskedastic. If you're not able to reject the null hypothesis, it means your errors are homoskedastic because the assumption is that all these coefficients are combinedly equal to 0. But if you are able to reject the null hypothesis, it means any of the coefficient, whether it is coefficient of y hat square or the coefficient of y hat cube and so on and so forth, any of such coefficients. So you run a regression. This is called a regression of UI on different non-linear powers of predicted values of y, then test for the joint significance of this entire model. I'm sure that once you talk about the joint significance, it involves a test which is your F test. So इसका एक बहुत ही simple rule उन्होंने decide किया कि जो इस model का R square होगा, the model R square, n times R square of this model will follow a chi square with degrees of freedom given by the number of parameters, number of observations in the model. And then you calculate chi square critical from the table and you calculate this n times R square. If this value is greater than chi square critical, you reject the null hypothesis. Rejection of null hypothesis means there is evidence of heteroskedasticity. If this n times R square is less than chi square critical from the table, it means you do not reject the null hypothesis. It means your errors are homoskedastic. Is this clear? Is this clear, guys?
Yes, sir.
Okay. Next test is your White's heteroskedasticity test. ये टेस्ट क्या है? ये भी टेस्ट on a similar line से Anscombe और Ramsey पे, but instead of running a regression on y hat, what it suggests is to run a regression of ui hat on ui hat square on different functions of the explanatory variable. So instead of running a regression of ui hat on y hat square, y hat cube and so on and so forth, White's heteroskedasticity test suggests running a regression of ui hat square on different functions of explanatory variables in the model. So, and when you run such a regression, they are called auxiliary regressions. So, uska regression kaisa dikhta hai? Suppose I have 3 variables in the original equation, then running a White's heteroskedasticity test will look like ui hat square beta naught plus beta 1 x1 plus beta 2 x2 beta 3 x3 beta 4 x1 square beta 5 x2 square, beta 6 x3 square, and then their combination as well. Beta 7 x1 x2, beta 8 x2 x3, beta 9 x1 x3, and so on and so forth. So you understand that as more and more numbers of explanative variables you have in the model, it becomes more and more cumbersome to write or to run an auxiliary regression for conducting a White's heteroskedasticity test. Again, the procedure is simple. You calculate R square from this auxiliary regression. N times R square from this auxiliary regression will follow a chi-square test. Again, you calculate chi-square critical from the chi-square table. You compare these two values. If N times R square, that is calculated value, is greater than chi-square critical, you reject the null hypothesis. It means your errors are heteroskedastic. And if N times R square, that is chi-square calculated, is less than chi-square critical, you do not reject the presence of homoskedasticity. In that case, your errors are homoskedastic. Is this clear?
Yes, sir.
Is this clear, all of you?
Sir, yeah, I understood the test, but I'm not sure why that should follow the distribution. I'm not still clear with that.
Why that should follow? R square क्या है, Neil?
Sir, it is ESS by degrees of freedom divided by TSS by degrees of freedom.
So it is sum of two independent chi-square distributions, right?
But sir, it's an F, right?
Correct. And when you multiply this R square by number of degrees of freedom, it follows a chi-square distribution.
Okay. But isn't that like a single value that we are getting?
Yeah.
Okay.
तो यही बात है ना भाई, sorry, ये chi-square calculated value of this regression, that is, ये आपका एक statistic है. N times R square becomes a statistic. It has a value. Now this N times R square, this follows a chi-square distribution. This
Okay,
entire.
sir. And we will compare this calculated value to the crit value, and then hello.
Can you all hear me?
Yes, sir, we can hear you.
Yeah. So N times R square follows a chi-square distribution. So you calculate this value and you compare it to the critical value.
All right, sir.
ठीक है? हाँ जी.
And sir, the degrees of freedom for the chi-square will be N out here.
Yeah.
All right.
Yeah. ठीक है? Okay. So we discuss Bruch-Pagan test when we go ahead. Let us talk about this Goldfleck-Korn test. What this test is valid for when you have smaller samples, like the examples that we had just talked about. So what this does is it divides the entire observations into two groups. One based on, let's say, lower or smaller values of x's, and one based on larger values of x's. Then you calculate the variances of both these groups and you compare the variances of these two groups. That is, you run a hypothesis in Goldfleck-Korn test as that of equality of variances of the two groups. If the variances from the two groups are equal, we reject the presence of heteroskedastic error terms. If the variances of the two groups are unequal, we say that error terms are heteroskedastic. And the likelihood ratio test is valid when you have large samples. इस केस में क्या करते हैं? First you calculate the variance of the entire sample. Then out of, let's say, n number of observations, you form one group containing, let's say, n1 number of observations. You calculate the variance of that group and you compare the variance of that group as a ratio of the variance of the entire group. That's why it is called as likelihood ratio test. We'll discuss all this. I'm just giving you a heads up that this is the test all about. So remember this Goldfleck quant test is much more easier to compute when you have a smaller sample, because in that case ranking of samples according to the values becomes much easier. Ramsey test and Anscombe test is based on the idea of running a regression of the estimated residuals on the estimated y values from the regression and their non-linear powers. White's test runs on the idea that you run an auxiliary regression consisting of regressing squared values of residuals on different functions of the explanatory variables that you have and also the interaction between them and testing the joint significance of the regression. Bruce-Pagan test almost runs on the same idea. It assumes that the heteroskedastic variance is some function, that is, it assumes that sigma square is sigma square fzi, where this zi is some variable which influences the error variances. And it does not matter what kind of functional form this is. So Bruce-Pagan test does not depend on the functional form of this relation. What it depends upon is the list of the variables which is thought to influence the error variances. So sigma square is, and this sigma square is called a scale factor. So sigma square is some function of zi which tends to influence the variance of the error term. And then you run a regression consisting of these zi. And then again follow the decision rule. We'll discuss this Bruce-Pagan test again next class. Goldfleck quant test valid for small sample. You rank the observations, you calculate variances of the two groups and test for the hypothesis whether the variances of the two groups are equal or unequal. Likelihood ratio test, when you have larger samples, you calculate variance of the larger whole sample first, then you take or you divide the entire groups into, let's say, N1, N2, N3 and so on and so forth, and then you calculate the ratios of the variances between them. Test for the examples that we have done today in today's lecture. What I'll ask you to do is read about these tests from the textbook Woolrich. Apply these tests on the example that we have discussed or that we have used for today's lecture. If possible, submit that to me. That is, which test gives you a better information about the presence of heteroskedasticity as far as this example is concerned. Again, I'm telling you, it need not be one particular test which gives you the best result, but out of all the tests, on the basis of what you have calculated, which test you think is the most suitable one. Is this clear? And why I'm saying that you must do it, because all these tests are based on running a regression. So आप और जितना भी आप टेस्ट देखोगे, they are running regressions of the estimated residuals from the regression that you have already done on various other functions. Run that regression, calculate the chi-square critical, chi-square calculated, compare to chi-square critical, and then take the decision rule. So, in particular, since the observations are very small in this particular example, run a Goldfleck quant test for this particular example. and also try whether you can run a White's heteroskedasticity test. And one more form of test which is often suggested is called your Gletser test, which is again running an auxiliary regression of UI hat on either 1 by xi or 1 upon root xi or mod of UI hat on the linear functions of xi in the model. It's a simple linear regression. You just include one explanatory variables at one time. You look at the R square of these equations and decide which equation gives you a better information about the presence of heteroskedasticity. Is this clear? What you have to do? So you can read Woolridge, you can read Johnston as well, econometric methods for these tests. Read those tests once. Now we have a gap of 1 week. I think next week you have your periodical, right?
Yes, sir.
Okay. Now tell me whether you want to do that periodical on R. All of you?
So can we have a test?
क्या बोल रहे हो?
So what will be the nature of the tutorial?
So what will be the pattern and syllabus, sir?
Yeah, so whatever we have discussed till now, except for the violation part, which is what we have discussed today, I'll give you one question. It will be a combination of 3 papers, so not everyone will get the same question. It depends on your, luck, which question one gets. So I'll prepare 3 paper sets. It will be one question consisting of all that we have learned so far, and you have to solve them or write a code for them on R and submit the solutions. Is that clear?
Like yesterday, not today's class is not included.
No, today's class not included.
Sir, will it be a test or assignment?
It will be a test.
And sir, regarding yesterday's class, I couldn't solve actually question 3. If you could give hint. I didn't understand question 3 that we don't solve in our own.
What you did not, what was there you did not understand there, Sharanya?
So I couldn't understand the difference between question number 2 and 3. Like question number 2, we have to predict the value and create the 90% confidence interval. And in question number 3 also, we have to predict the average sales for 2 years when the advertisement expenditure is 600. So basically average sales for 2 years will be the same sales per month, right? So basically the answer would be the same. I didn't understand what's the difference between question number 2 and 3.
Yeah, you see, as far as prediction of average value and actual sales value is concerned, the prediction value will be same, but the confidence interval will be different. You see why? Because when you talk about prediction of actual values of Y, you're talking about Y not or Y not hat, whatever term that you use. So in that case, the prediction error becomes Y naught hat minus Y naught, and Y naught is the term which contains error observation. But when you talk about prediction of the average value of Y, in that case, what you're talking about is expected value of Y and uska average, that is expected Y ka hat. Do you understand this part?
Yeah, but
so expected Y hat will not contain a term of U. You're not getting what I'm saying?
No, sir.
So,
Yeah,
so we have microeconomics right now. So,
just give me 2 minutes.
ma'am, okay.
Sir, ma'am has come in the class.
ठीक है फिर आप जाओ.
Sir,
Yeah.
sir, about the test, can we have it like a one-day assignment?
But why?
Sir, because we are not very comfortable with R right now. We did 2 classes, so that's why. Like one day
sir,
assignment if
secondly,
possible.
one thing is, like I and many people live in Kolkata and Orissa, and a cyclone is about to hit, so we don't know about network issues, what we will face. So, like, if it would be an assignment, it would be very helpful actually, because we don't know how network issues are going to be on that particular day. It's about to hit in 2 days, and the exam is like in 3-4 days, and we don't know how long it will take to restore the network, because in Amphan it took around 1 week.
अच्छा.
That was a big problem
And we also have mailed our coordinators, but we haven't heard.
Yeah.
अच्छा, okay. ठीक है. In that case, that makes sense. But Sidhu, I think ये सही नहीं है यार कि you're not that comfortable. You have 1 week time. This I agree regarding the cyclone issue. But 1 week time, you can practice a lot as far as many questions are concerned.
So we already have 3 tests, 3 tutorials on Monday and Tuesday.
Okay, I'll say. You talk to the coordinator whether they are comfortable with having assignment. I have no issue.
Okay, sir, I will get clarified with Swati ma'am.
हाँ, एक बार आप उनसे बात कर लो, लेकिन ये प्रैक्टिस कम होने का बात प्लीज मत करो. या तो
Okay, I won't say that, sir. But Sharanya's topic, I yesterday got to know about this. I was not aware. That was also there.
Yeah, we all actually mailed the coordinators, but we haven't heard from them yet.
ओके, सेतु आप प्लीज एक बार स्वाति मैम को कॉल कर लेना.
Okay, sir, I will inform you what she tells about.
हाँ जी, एक बार आप कॉल कर लो उसे, and then just tell her कि this is the actual problem and what do we exactly do.
Okay, sir.
So in that case, अगर वैसा होता है तो I have no issue. We can easily go by that.
Okay, thank you, sir.
ठीक है. हाँ, coming back to your question, Sharanya, can you see the screen?
Yes, sir.
Okay. So prediction of average value means you're talking about this. Prediction of actual values means you're talking about this. So expected value आप कैसे लिखते हो? अगर आपका population regression है, मान लो. Actual average value of the population will be this, right?
Yes, sir.
ठीक है. और expected average value क्या होगा? Correct?
हाँ, yes, sir.
So इस केस में prediction error क्या होगा आपका?
B naught, the error term B naught minus B1 minus B1. Yeah, okay.
Right?
Yeah.
So जो ये जो plus एक error term था, that will not be in this expected case.
Okay. So basically, we must calculate the variance again, and then we have to.
Correct. So it will have a lesser variance. So when you are actually predicting about the average sales value, then the confidence interval that you generate are narrower. But when you actually predict about the actual sales value instead of actual average sales value, then your confidence interval is wider, because the variance in this case will be smaller.
Yes, I understood now. Okay.
ठीक है?
Yes, I got it. Thank you.
Okay, all right. ठीक है, so I stop here. In the meantime, what I'll request you is to जो भी आज हमने test discuss किया, I'll share the code file that we have used for today's lecture. Second thing, I'll also, I think Neil had shared with you the notes.
Sir, you are audible.
So we
So
can't
we
hear
lost.
you.
We can't hear you.
Yeah, can you hear me now?
We
Yes,
can
sir.
hear you, sir, now.
Okay. So Neil had shared the notes with you guys, right?
Yes, sir, we did.
Yes, sir.
Okay, all right. So go through the notes which talks about heteroskedasticity theoretically. So read those notes. नोट्स के बाद या नोट्स के पहले अगर आपको बुक पढ़ना है तो यू कैन रीड बुलरिच or Johnston, whichever book you find easier to read, and then apply those tests. At least apply Goldfleck Korn test and White's test on the example that we have used for today's lecture. Is that fine?
Fine, sir.
Okay, sir.
Okay, all right. And in the meanwhile, Setu, please talk to Swati ma'am and let me know उनसे clear करके. अगर ऐसा है तो assignment I'll give.
Okay, sir.
ठीक है. Yeah. Okay, then, all right. We'll discuss about heteroskedasticity again in the next class, and then we finally talk about remedial measures and all in the next class. So, some other violation around it will take at least 2 to 3 weeks to complete about violations. At least month of June will, by the end week of June, we'll start with time series and other things. And before that, we'll try to complete violations and remedial measures. And once we complete this portion, it will be much easier to move ahead. So we'll discuss about heteroskedasticity test. I'll discuss again, and then we move to understand the remedial measures, and then we talk about autocorrelation and other functional, other specification errors. Okay?
Yes, sir.
All right. Thank you so much. And those of you who are getting late for microeconomics class, please go. Thank you so much. We'll meet next. Monday. If you do not have.
So we have to cancel. So we have to note the day.
So,
Monday, Tuesday.
but next week, guys, I'll take lecture, beat extra lectures, but I have to take. Otherwise, problem ho jayega. So be prepared for extra lectures next week for sure. This week I'm not arranging because many of you will say that I'm preparing for tutorials and all. But next week I'll have. So if not on Monday, Tuesday, definitely Wednesday, Thursday, Friday, Saturday, Sunday is 5 दिन में से कोई भी 2 दिन I'll have lectures with you. Okay?
Okay, sir.
Okay.
All right.
Thank you, sir.